All right. There we have it. So, can you all see my screen right now where it says Introduction to Lipids? Can everybody see that? Thanks, Tyler. Great. Okay, good. As long as one person can see it, that must mean everybody else can see it. Okay, so let's get started on lipids. And it says here in the introduction to lipids that lipids are biomolecules that are soluble in organic solvents and insoluble in water. When it says organic solvents here, you kind of have to take that with a grain of salt. And what they mean is non-polar organic solvents. Things like hydrocarbons, like maybe hexane, benzene. These are common nonpolar solvents in organic chemistry, toluene, etc. Anyhow, the main thing that you have to understand is that we're talking about nonpolar organic solvents and that they are insoluble in water. So lipids are actually not defined by a particular functional group, and thus they have a variety of structures and functions. And if you think about what we've studied so far in this class, every chapter dealt with some kind of functional group or multiple functional groups. Let's say we did a chapter on carboxylic acids and esters and acid chlorides. Then we did another chapter on alcohols. Then we did a chapter on aldehydes and ketones. But lipids are not defined by any particular functional group. In fact, we're going to see several functional groups show up in this chapter. We will see esters, and we'll see phosphate esters, and we'll see amines, and we'll see carboxylic acid. So we'll see several functional groups. And finally, the last bullet point here says lipids contain many nonpolar carbon-carbon and carbon-hydrogen bonds and very few polar bonds, resulting in their water insolubility. So just like we saw in hydrocarbons, which only possessed carbon-carbon and carbon-hydrogen bonds, lipids might not only contain those bonds, but they contain many of those types of bonds, and therefore it decreases a lipid's water solubility or a molecule's solubility in water the more carbon-carbon and carbon-hydrogen bonds we have. And just as a quick review here with respect to carbon-carbon and carbon-hydrogen bonds, the difference in electronegativity of two carbon atoms, one has an electronegativity value of 2.5, the other one is 2.5, so I get a value of 0 there, so that's definitely nonpolar. And for carbon-hydrogen, I get a difference, or a delta En of 2.5 for the carbon minus 2.1 for the hydrogen. That gives me 0.4. And if you remember, the cutoff for a bond being a nonpolar bond meant that the change or the difference in electronegativity had to be less than 0.5 units. So again, we're going to see a lot of nonpolar bonds in lipids. Our textbook goes to great lengths to find all manner of ways to categorize lipids. But let me just explain what she means by some of these categorizations. So the first one, she says you can categorize lipids as being hydrolyzable lipids. And hydrolyzable means they can be broken apart by hydrolysis, right? Hydrolysis is water, and lysis means breaking. So literally breaking molecules apart by the addition of water. And the types of molecules that we're going to see that can be broken up by hydrolysis are waxes. And waxes are nothing more than really just kind of like giant mammoth-sized esters is really what a wax is. So we're going to see the functional group, the ester group that can be hydrolyzed, of course. And then in what are known as triacylglycerols, sometimes we call these triglycerides. Sometimes we call them TGCs, triglycerides, or triacylglycerols. We're also going to see ester bonds in those. And then finally, in phospholipids, we're going to see ester bonds in those as well. I'm not saying that every one of these are esters. All I'm saying is that we will see ester functional groups that are hydrolyzable in waxes, triglycerides and what are known as phospholipids. The next one is we can categorize lipids as being non-hydrolyzable, and that means they cannot be broken apart or they cannot be cleaved. Cannot be cleaved by aqueous hydrolysis. And the class of compounds that would fall in here would be what are known as the steroids, and you're probably aware of anabolic steroids, right? If you've ever heard of bodybuilders and those kinds of things who might use steroids, or maybe athletes. But cholesterol is a steroid, and we're going to look at the structure of steroids, and we're going to look at the core structure of steroids, and we're going to see what all steroids have in common. If you've ever studied biology, you might have memorized the fat-soluble vitamins, which are vitamin A, D, E, and K, and so all of those are fat-soluble, therefore they're non-polar, but they're non-hydrolyzable. And finally, the eicosanoids. Eicosanoids, eicos stands for 20 carbons, so we're going to look at a few different compounds that have 20 carbons in them, and we will look at what are known as the prostaglandins and thromboxanes and some other interesting molecules that we won't go into nearly as much detail in. And here we go. This kind of kicks off the beginning of chapter 17. That was just kind of an introduction that I put together. Anyhow, so as an energy source, lipids provide 9 kilocalories of energy per gram of fat. And if you think about, going back to introduction to chemistry, you would have learned that carbohydrates, so carbs and proteins, both provide around 4 kilocalories per gram. And so lipids or fats provide much more energy than carbohydrates or proteins do. And the reason why is because of the combustion of all of those carbon-hydrogen bonds. When you think about human beings, really what we are is just big combustion chambers, Anyhow, there we go. So the next one is triglycerides provide energy storage in adipocytes, which are fat cells. And these fats, meaning triglycerides, are a particularly rich source of energy for the body. Then in terms of steroid hormones, so the steroid hormones are critical chemical messengers that allow tissues of the body to communicate with one another. And we're going to look at prostaglandins, which are hormone-like molecules that can exert strong biological effects on both the cells that they are produced by and other cells in the body. Then, of course, the lipid-soluble vitamins, A, D, E, and K, they play a major role in the regulation of several critical biological processes, including blood clotting and vision. What else? Let me move down here. The next one, it says dietary fat acts as the carrier of lipid-soluble vitamins into the cells of the small intestine. And of course, we use them for protection as a shock absorber or a protective layer over our vital organs. And of course, insulation, the fat stored beneath our skin, which is called subcutaneous fat, serves to insulate our bodies from extreme cold temperatures. Anyhow, there we go. Let's move on and talk about classification of lipids. And this is kind of what we're going to look at next, are going to be the fatty acids. And there's two main types of fatty acids. And I'm sure you've all heard of saturated fats and unsaturated fats. And so we'll get to the bottom of what that means tonight. And you've probably already heard me talk about fatty acids. And generally speaking, a fatty acid is just when we have a carboxylic acid, but instead of having a short R group, like in acetic acid, we have a long group. So we have many carbons on the end like this. Okay, so we have many carbons, and that is what makes a fatty acid. If we have no double bonds in the chain here, the big long tail, if you will, we call those saturated fats. And when we do have double bonds, we call those unsaturated fats. And so tonight, we're going to get to the bottom of cis and what are known as trans fats. I'm sure you've all heard about trans fats, which are kind of, they were big in the news not that long ago because of the connection to atherosclerosis. The next one, it says glycerides are glycerol-containing lipids, and these could also be phospholipids or sphingolipids, and we'll take a look at that. The next one, it says here, the non-glyceride lipids like sphingolipids, steroids and waxes, and then complex lipids, which is lipoproteins, and we probably won't get into that this evening. That's kind of towards the end of the chapter. You know, like I told you at the very beginning, she goes through great lengths to find all kinds of ways to classify lipids. And this slide isn't in here to, you know, make you intimidated about lipids. It's more just to kind of let you know, lipids it's a big umbrella, right? It covers a lot of different types of molecules, and we're going to look at many of these. We're going to spend some time looking at saturated and unsaturated fat. We'll look at neutral glycerides. We'll look at sphingolipids, steroids, waxes, lipoproteins. Anyhow, so we're going to try to cover as much ground as we can. So let's get started in talking about fatty acids. And this is section 17.2 in our textbook. I'm just going to move this down a little bit so I can draw the generic structure of a fatty acid so that we can think about it while we're talking about it. So I have my carboxyl group here. So I'm going to put 1, 2, 3, 4. There we go. So this is a fatty acid that I have drawn here. And you can see I have a total of 18 carbons, and you don't have to worry about that right now. But what you need to know is that this portion of the molecule here, right, this is going to be water-loving, or what we call hydrophilic, okay? So that part is going to be able to participate in hydrogen bonding. You could even draw a water molecule and practice your hydrogen bonding, drawing skills, but I'm going to just not do that right now. And then we have this big long hydrocarbon chain, okay, over here. Now I didn't say the molecule is a hydrocarbon. I said the chain is a hydrocarbon, and this chain would be what? It would be hydrophobic, right? Hydrophobic. It's going to be not water-loving because it contains so many of those carbon-carbon and carbon-hydrogen bonds, right? Which we said are non-polar bonds. Okay, so long straight-chain carboxylic acids, that's basically what a fatty acid is, and we don't have any branching coming off of the chain. So no branching, and we could even add here, no branching off of the chain. So what that means, if you're like, what do you mean by that? Okay, all that means is you're not going to see, methyl groups or something like that. That's not going to happen, so I'll delete those. Most common chains range from 10 to 20 carbon atoms in length. And what's interesting is that, you are expected to memorize the number of carbons, which is, and I just mean generally speaking, the range would be from 10 to 20, but also it says here that it's usually an even number of carbons. So that means you'd have either, you'd have 10 or 12 or 14, so on and so forth like that. Okay, and that includes the carboxyl carbon. Let me double check here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18. Yeah, so the one that I've drawn here has a total of 18 carbons, including that carboxyl carbon. Now it says here that carboxylic acid fatty acids can be saturated or unsaturated, but usually we have no other functional groups present. So we're not going to see aldehydes or a thiol showing up here. We're just talking about the carboxyl group from the carboxylic acid and then the big hydrocarbon tail. It says here that any fatty acid that cannot be synthesized by the body is called an essential fatty acid. And again, if you've ever studied biology and ever spent any time studying amino acids, you've probably heard of essential and non-essential amino acids, and you've probably also heard of complete and incomplete proteins. And so essential fatty acids are just like essential amino acids, and that those are the ones that we are unable to make, and they must be taken in through our diet. A little bit more about the structure here. So that carboxylic acid, or that fatty acid that I had drawn on the previous slide, I drew 18 carbons deliberately because I wanted to draw stearic acid. And stearic acid, what do you think of when you hear the word steer, right? You probably think of, well, steer a car, I suppose, but you might think of a bull, or some kind of something from the bovine family. And so stearic acid is a fatty acid that comes from the hydrolysis of beef fat, which is tallow, and I'm sure it's found in other places as well. But stearic acid, it says, is a typical saturated fatty acid with 18 carbons in the chain. And you can spend the time counting them if you feel like doing that. But what I really want you to focus on right now is the saturated part, okay? Now, if we think about that saturated, what that actually means is that there are no double bonds, in the chain, okay? Because if you're like, well, there's a double bond here, yes, I see that, but I'm talking about the hydrocarbon chain, okay? So there's no double bond in the chain, whereas if we take a look at oleic acid, it says it's a typical unsaturated fatty acid. Why is it unsaturated? Because you can tell right there, it's got a nice, tasty double bond in it, okay? So it says here that oleic acid is also a fatty acid with 18 carbons in the chain, but it is unsaturated. Why? Because it's got a double bond. We could even write that down. We could say here unsaturated, well, we could say unsaturated, okay, has double bond, okay? So let's just scribble that in there. It has a double bond, right? Something else that's interesting, and this is on a slide coming up, but if you count the carbons starting with the carboxyl as 1, 2, 3, 4, 5, 6, 7, 8, and then 9 and 10, what you'll see is that oftentimes in unsaturated fatty acids, the first double bond will be at carbon 9. I know you're like, what, carbon 9? Well, I didn't invent evolution, okay? Yeah, anyhow, I'm just teaching the class. Anyhow, so it says here, this is just kind of a summary to help us out a little bit. The saturated fatty acids, we see no double bonds. Unsaturated fatty acids do contain double bonds. But what else did you notice about that double bond? Let's go back. Let's go back to that double bond that I had circled in red. And I'm sure you all know what the answer is to what I'm going to ask is this a cis or a trans double bond? Who could tell me? Cis or trans? Yeah, thanks. It's a cis double bond. Yeah, thanks, Tyler. Good. It's a cis double bond, right? How did you know that? Because the two hydrogens, right? The two hydrogens, oops, where's my pen? These two hydrogens here are on the same side of the molecule, and therefore it's a cis fatty acid. Kind of interesting, huh? So you're like, where are the trans fats? I want to hear about those. Yeah, so it says here the double bond is actually normally in the cis configuration. So most unsaturated fats, virtually all natural unsaturated fats, are cis fats, okay? And we'll talk about the cis fats in a little bit, but let's talk about what the effect is of the double bonds, okay? So if we think about the ability of molecules to pack together to maximize their London forces, it says here that the double bonds lower the melting temperature because the cis configuration does not allow fatty acids to pack as close together. Well, that seems reasonable to me. If you back up and look at these two structures. If you were to draw a bond line structure of stearic acid, which I did back here, okay, at the top of the slide, if I was to draw two of those, you can see that those would pack together quite effectively, okay? Whereas if once we get that kink or that bend in the molecule that's seen here in oleic acid, well, two oleic acid molecules are not going to pack together or interact together nearly as effectively as two molecules of stearic acid, which is a saturated fat. And that's why saturated fats are usually solids at room temperature. If you think about fats that come from animals, like beef fat or fat from bacon or something like that, those fats are normally solids at room temperature, right? You can heat them up, of course, and melt them, but they will usually solidify, right? If you make some hamburger or something, you strain off the fat, it will solidify, okay? Whereas canola oil contains fats, right? But that fat comes from a plant, right? And those are unsaturated fats. And because those molecules can't pack together as effectively, they are normally liquids at room temperature. So let's see what it says here. It says an unsaturated fatty acid has one or more carbon-carbon double bonds in the chain. The first double bond, like I told you before, is usually at the 9th carbon. Just kind of an interesting factoid that you should be aware of, that this is normally carbon number 9, right? The Beatles wrote a song about it. The double bonds are not conjugated. Now, I don't remember if you guys, are aware of what conjugated is. I think I told you. Conjugated means when you have a double bond, then a single bond, then a double bond, then a single bond, then a double bond, then a single bond, then a double bond, right? That's conjugated, okay? Is when you have double and single bonds alternating. So you can clearly see that this is not conjugated to any other double bond. And it says here that cis double bonds result in a bent chain and lower melting point or decreased London forces. I'll tell you what's really funny. Now, I haven't taken a whole lot of time to make that many fatty acid molecule models in my life because it takes so many stinking atoms to make it. But I can tell you that I have done it. And if you make a chain of 18 carbons in the saturated fat, I mean, you can get that to be in a nice, beautiful straight chain. But as soon as you put a double bond in there, the molecule becomes really cumbersome. It's harder to hold, it's harder to manipulate, it starts falling, not necessarily falling apart, but you can see how much more difficult it is for the molecules to pack together. So this molecule that's shown down here has a cis double bond. It's a cis fat, and it's called palmitoleic acid. What else here? It says fatty acid properties. I think I put some space in the top here because I had some machinations about drawing a fatty acid again, maybe. 1, 2, 3, 4, 5, 6, 7, 8, 9, oops. 9, 10, 11, 12, 13, 14, 15, 16. Let's draw a 16 carbon fatty acid. Again, here's our carboxyl group. This is why they call it an acid, right? It's because it is a carboxylic acid. And then this is where the word fatty comes from, right? Because fats contain mostly carbon or carbon-hydrogen bonds. Anyhow, what else do we have here? It says that melting point increases with an increasing number of carbons. Well, that makes sense because we're going to get increased London forces, right? We're just going to get more interactions as we increase the number of carbons. It also says the melting point of a saturated fatty acid will be higher than that of an unsaturated fatty acid with the same number of carbons. I'm not going to go over that again, but I'll just say, why is that? It's due to the efficiency of packing. A saturated fatty acid packs more efficiently, therefore it has more London forces, and therefore a higher melting point, or it takes more energy to convert that solid into a liquid. Typical saturated fatty acids are tightly packed together, of course. Cis double bonds, this is another way of putting it. Maybe this is more eloquent than how I can do it off the cuff, but it says cis double bonds prevent good alignment, okay, or of molecules in unsaturated fatty acids, leading to poor packing, and the double bonds will, of course, lower the melting point relative to the analogous saturated fatty acid. This slide just shows kind of a comparison of some saturated and unsaturated fatty acids. Let's start with the set that's at the top. So this part right here, these are all saturated fatty acids. And we go from decanoic acid, which has a total of 10 carbons, and then dodecanoic, which has a total of 12, then tetradecanoic, then hexadecanoic, octadecanoic, and then icosanoic. Didn't I tell you earlier that icos means 20 carbons? Anyhow, I'm sure that there's somebody online right now who's wondering, do I have to memorize all the names of those saturated fatty acids? Of course not. No, you do not have to memorize those. You just have to understand what the heck is going on here in the trend. And the trend that we're really interested in is this trend right here, is the trend in melting point, and that the melting point increases, right, gets higher and higher and higher as we increase the number of carbons. And why is that? Well, anybody I'm sure that's online could explain that. It's because of what? Increased London forces. Nothing more than that. Okay, if we look at the next set, it says common unsaturated fatty acids. Now we have to count up, we have to, what's the word I'm looking for? We have to take into account the number of carbons plus the number of double bonds, and well, not so much the position, but we have to take into account the number of double bonds. Anyhow, let's compare these three in the middle, okay? Because these three virtually all have the same mass, right? Between 282 and 278. That's pretty stinking close, okay? So we're going to look at oleic, linoleic, and linolenic acid. What do you think of that one, huh? Linoleic and linolenic. Okay. Again, I didn't come up with the names. I just, like talking about them with my students. Anyhow, so if we compare these three, they all have very, very similar molar masses. So we'll put close, very close. Okay, but look at the difference in the melting points. The melting points decrease. So we could put here melting point. So we could put here increased. There must be increased London forces on the top, right? And because the melting points decrease as we go down. Well, let's see. Why would that be? Why would the melting points decrease? Well, look at the number of double bonds. Okay, we're increasing the number of double bonds, and what that does is that makes it more and more difficult to pack these molecules together. So what's the conclusion from this section? Is that the more double bonds we have, right? What I'm talking about is this right here, the more double bonds we have, what's going to happen is the melting point is going to get lower, right? And it's because of decreased London forces. The last section just deals with some condensed formulas. You can take some time to look at that if you want, but I think the most effective way to draw fatty acids, whether they be saturated or unsaturated, is to use the bond line structure. All right. If you're the kind of person who can't live without a graph, if you can't sleep until you look at a graph, well, here you go. As a wise man once said, here it is, come and get it, right? So here's the temperature on the y-axis over here. And then we have the number of carbon atoms on the x-axis down here. And for now, I just want to start by focusing on this line only. Okay, I just want to look at this line only because this line is only a plot of number of carbons versus temperature for saturated fatty acids. What's the conclusion? I bet you anybody who's online could explain the conclusion. Is that as the number of carbon atoms gets bigger and bigger and bigger, what happens to the melting point, right? It goes up, 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 up. It just climbs, okay? And why is that, right? It's just because of, we could put here increased London forces. Nothing more complex than that. Now I want to focus on another line. So I'm just going to delete this one for now. I want you to focus on this line right here, this vertical line, because every single one of these molecules that's on this line has 18 carbons. But what happens is, as we increase the number of what? Double bonds, what happens? The melting point drops. And we could even write here, let's write in brackets, 0 double bonds. So as we go from 0 to 2 to 3, what happens is our melting point decreases. And again, it's just because it's harder and harder for the chains to pack together effectively as we increase the amount of unsaturation. Give me a thumbs up if you follow me so far, or a hey, or a man, I love organic chemistry, or this is the greatest summer of my life. All right, I'll take it. Thanks, Tyler. Okay, so let's talk about omega-3s. I'm sure you guys have all heard of omega-3s and omega-6s, okay? You want me to make it really simple for you? So it doesn't matter really how many carbons are in a fatty acid, okay? There could be 10, 20, 16, whatever. It doesn't matter. You go to the terminal carbon. So the carbon, what do I mean by terminal? I mean the one at the end, okay? You go to the carbon at the end, and that's called the omega carbon, okay? So this is the Greek letter here. Maybe that wasn't the best drawing of it, was it? There we go. This is omega. That's little omega. Little omega. You might have, you probably all own an omega watch, which is the capital omega. That's omega. Trust me, Mr. Deon doesn't have the whole Greek alphabet memorized. Anyhow, so an omega-3 fatty acid, what you do is you go back 1, 2, 3 bonds from the omega carbon. And if there's a double bond, it's called an omega-3. Let me show you. So if you start here, so I'm starting on carbon 18 on ALA, you go 1, 2, and then on the third carbon, there's a double bond here. Boom, that's an omega-3. That's all there is to it. Nothing more, mind-boggling than that. Anyhow, there's a bunch of omega-3s on here. I'm not going to try to read all of their names. They have nice clean and tidy acronyms for people who study these kinds of things for a living: ALA, EPA, and DHA. And these are found in oily fishes like herring and in flaxseed and canola oils, and have been recommended as part of a healthy diet. Now that I live in Colorado, I don't eat nearly as much fish as I used to when I was up living next to the St. Lawrence River. Anyhow, just a little bit of, kind of FYI about omega-3 fatty acids, the three fatty acids that were shown on the previous slide. It says that their research has shown that they are involved in reducing the risk of cardiovascular disease by these factors here: decreasing blood clot formation and lowering TGC levels, and decreasing the growth of atherosclerotic plaque. If you've ever heard of hardening of the arteries, this is where we have plaque buildup inside of our arteries. And so what the result of that can be hypertension, which is high blood pressure. So basically these will help you to maintain proper blood pressure. Anyhow, it says here that due to these effects, arterial health improves, blood pressure is decreased, as does the risk of sudden death and heart arrhythmia. So eat those flax seeds, I guess. Anyhow, you've probably also heard of omega-6s, and it says here there are also some omega-6 fatty acids that are an important part of the diet. So you've seen one of these already tonight, or I mentioned it, which is linoleic acid. This here, and you can see why chemists have developed common names for these fatty acids, because you can imagine that if you worked with these every day, that naming something like cystis 912 octadecadienoic acid might get a little bit cumbersome after a while. Anyhow, so an omega-6, we take the same approach to determine whether a molecule is an omega-6 as we did with an omega-3. We go to the terminal carbon. That's the one here at the end. So there's our omega carbons. Then we count back. 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6. On the sixth carbon back, we have a double bond, and therefore this is an omega-6. We could try it here too. We could go 1, 2, 3, 4, 5. On the sixth carbon, what do you know? We have a double bond. Now keep in mind, we're not using the proper numbering system for nomenclature, right? Notice that the nomenclature, they were very careful, to point out that the carbonyl carbon is carbon 1, and then they put the alpha carbon in, and then beta, whatever. But when we're determining whether a molecule is an omega-3 or an omega-6, we start with the last carbon, and we call that number 1, and we just count back. What else does it say here? Linoleic acid seems to reduce the incidence of CV, or cardiovascular disease. Linoleic acid is also an essential fatty acid required for the synthesis of arachidonic acid, the precursor for many prostaglandins. I'm just going to bring this molecule to your attention. If you ever decide to study biochemistry at the full semester university level, maybe a 3 or a 4,000 level class in your 3rd or 4th year university, arachidonic acid is a very important molecule in biochemistry. And in order to understand the synthesis, like it says here, of prostaglandins and other molecules, you have to learn quite a bit about the chemistry of arachidonic acid, which would be beyond the scope of our course. But I'll just leave that there. Arachidonic acid, a very important fatty acid. Just give me 1 second here. So all I'll say here is that the eicosanoids, like arachidonic acid, contain 20 carbons. So like I said, eicos stands for 20. And it says here that eicosanoids are 3 groups of structurally related compounds. The prostaglandins, or what we call sometimes the PGs, so we could put that in here, the PGs, the leukotrienes, and the thromboxane. I've never asked a question about either of these in the entire 11 semesters that I've taught Chemistry 102, so I wouldn't stress about the leukotrienes, or the thromboxanes a whole hell of a lot. All right, prostaglandins. Just give me 1 second here. Sorry.